I know yesterday we kind of got halfway through this question, so let me just kind of catch up to you guys. So we took the polynomial and we graphed it, and we figured out some x-intercepts that would work. Had to do a little bit of investigating, and after doing some synthetic division, so we did 2 levels of synthetic division, right, with -3 and -1.25.
Your screen's
Aw, dang. I am over here. Alright, so we ended up with a quadratic down here that was, what was it, 4x squared minus 32x plus 164. Cool. Alright. And I think that's kind of where I left you guys yesterday?
Yes.
Okay, so there's 3 questions up at the top of this problem where they want you, why is nothing working here? I'm so confused. There we go. They want you to answer them. And the first question says to write as a product of linear and irreducible quadratics. So, I think it's f of x, not p of x, but whatever. Which we could do right now with a little bit of investigation, but I'll be honest, when I answer this question, I like to answer the last question first. So the last question says, find all of the zeros of your polynomial. Now guys, with this being a degree 4, we're supposed to be finding 4 solutions. And right now we have 2. We have 2 from our work on our calculator / synthetic division confirmation. You have an x-intercept at -3. You have an x-intercept at, you can call it -5/4 if you'd like to call it a fraction, which most people do. So where are these other 2 x-intercepts or zeros coming from? Well, they're going to have to come from the quadratic you just reduced down to. So, I'm going to need a little bit of space here. Let me get some work down here. I'm going to take that quadratic, and I'm going to think about solving it. Well, how do you think you want to solve this quadratic? The quadratic formula? Yeah. Did anyone see that there's a common 4 here? So we could just divide the 4 out of it. I'll come back to that topic in a minute. This is usually where kids mess up. Talk about why. Alright, so the reduced quadratic, if you're trying to solve it, becomes this. And then I totally confirm that, yes, I agree with you, Daniel. We're going to have to use non-factoring methods because this is not going to factor. So quadratic formula would be 8 plus and minus the square root of, let's see, 64 minus 4 times 1 times 41. That's gross. Alright, all over 2 times 1. So the discriminant, if you were to type that in your calculator, doesn't come out to like a -100. Yes.
Is discriminant, it's what's under
Right.
it, not after you take the...
Right. The discriminant is the value of the algebra, or the calculation underneath, just the b squared minus 4ac part.
Okay.
So we have 8 plus and minus. This is the square root of -100, because the discriminant's -100. What's another name for the square root of -100? 10i. So we have 2 solutions. We have x equals 4 plus 5i and 4 minus 5i. Ooh, that's a 5. So up here where they were saying like give me all your solutions, like here you go. So when I go back and I look at that graph on the calculator, why was I only seeing 2 of them and not all 4 of them? Because these 2 are imaginary, and therefore you're not going to see them crossing the real x-axis. They would be something else. All right, so I just found my 4 solutions. Yes.
Those up at top, those graphs are a graph of this.
Yeah. So you only see 2 real solutions.
So,
but we know there's actually 4.
right. So just curious, and if you don't want to answer this question, it's too deep, that's fine. But like, I was watching this video about imaginary solution and how it like comes off the graph. Like,
yeah.
And it showed that like it kept going like at like an angle.
Yeah.
So does
there's
it
a
also
complex
go up
plane.
at an angle upward too?
So
across the plane again?
if I want to graph, so it's a matter of converting. It's like just like with anything in math, you can convert from one system to the other. So like the imaginary number 4 plus 5i, or the complex number 4 plus 5i, if I wanted to transpose it to a Cartesian coordinate plane, which is this guy, it's located what we know as 4, 5. So like the imaginary axis is the vertical axis.
Okay.
So the visual representation for it's a little deeper than that. But like if you're trying to convert, like how does this look? At what we know as the ordered pair 4, 5 would be the representation for 4 plus 5i.
Okay.
That's a good question. Very complicated stuff. It's like next level math.
Yeah.
Look at you thinking deep on a
knew
Tuesday.
that,
All right, so here's where you can go back and you can answer either one of these questions now. I would go back to A, and it says write them as a product of linear factors or irreducible quadratics. Now, knowing the nature of my quadratic solutions we just found, these were not factorable quadratic solutions, right? So when they say irreducible quadratics, they're referring to this guy. But this is where kids mess up. So they're like, oh, can I write down x squared minus 8x plus 41? No, because what was that originally? It was this blue thing. So I get kids who lose their coefficients because they pick up the wrong quadratic. So keep the entire quadratic. We'll talk about another option in a minute.
Doesn't that mean the same thing?
Where'd your 4 go would be my question. If you wrote down the x squared minus 8, well, hold that thought, Danielle. I'm going to come back to it, okay? So you guys had two solutions that you stole from the calculator, right? You had x equals negative 3. So your factor would be x plus 3. And then this guy, this negative 1.25, I'm choosing to write it as a fraction right now. And I'm going to write your factor as x plus 5/4. Now, we had this discussion the other day where some kids were like, wait. I've never seen x plus 5/4 as a factor. Like usually it's like a coefficient, like 4x plus 5 is how that factor would look. Let me show you how that comes up. What if you took the 4 out of this? But you still left it there for a minute. So now you'd be left with this x squared minus 8x plus 41. And then what if you took this 4 and you applied it to this factor right here? Because you can always multiply coefficients into a series of factors like this, but you have to be choosy where it's going. It can't go to all your factors because then you're multiplying by multiple 4s. So you could take that 4 and you could throw it into this factor right here. So it's not here anymore, it's gone. So then you'd have an x plus 3, and this would become a 4x plus 5. This is equivalent to this. Here's how I'm going to prove it to you. What's your lead coefficient on this one? This is a 4x squared times an x times an x. It is a 4x to the 4th. What's your lead term here? X squared times x times 4x. That's a 4x to the 4th. What was the lead term on your original polynomial here? 4x to the 4th. So here's what I get from kids sometimes. They'll either 100% lose the 4, like it's off their paper and never coming back, which tells me that they weren't watching their lead term test at the end of this problem. So when this problem comes up on your test, it won't happen this Friday, but next Friday. When you're all done with it, you got to make sure that your lead term matches what the original lead term was. So there's a lot of algebra that's going to happen in this problem, and a lot of like misconceptions that happen because you're so used to just like canceling the 4 and be gone with it. Well, you can't change the polynomial. It has to be there somewhere in your work. All right. This is the one no one likes. So you're going to take all 4 of these icky numbers and you're going to just write them as factors because the directions on part B say write as a product of linear factors. You're allowed to have disgusting factors when they say that. So you're going to write f of x equals the boring ones, x plus 3 times, you can leave it as x plus 5/4. Beep, beep, back up. I wrote all over my problem. Now, these icky blue ones, x minus, when you have a binomial solution like this, you got to put it in another set of parentheses. Yuck. And then x minus, and then you have another binomial, so 4 minus 5i. Don't try to simplify that. However, I would argue that we've done something wrong. My lead term right now is x times x times x times x. I'm missing the 4. So I either need to just stick it in front of my problem like this, and therefore I have a 4. What else could I have done though? I could have put it into this weird funky fraction one and called it a 4x plus 5 instead.
Well, could have put it anywhere.
I could have put it anywhere, yeah. I could have made this a 4x plus 12. That'd be weird though. Okay. So that's kind of gross. We'll do more of those. before we test on next Friday. This stuff is not on this Friday's test. It's on next Friday's test. All right. Get out your next lesson, guys. This is graphing rationals. And this lesson is on worksheet 9. You're going to use that yellow card when you picked up, when you walked in. Whoops. And Mrs. Hoffbar put a lot of care into making sure that these steps on your yellow card are in a logical order for how we have to answer these questions. So every time we talk about like, okay, let's do these questions, I want you to stick with the same order that's on your yellow card here. For my Honors Algebra 2 kids, you have a little brief introduction into graphing rationals. My regular Algebra 2 kids have never seen this before, so we need to kind of start from the basics, all right? We're going to be graphing rational functions, and they look very weird. They have asymptotes in them. Sometimes they have holes in them. But we're going to be finding a lot of features, and on your no calculator test on Friday, you're going to be finding all of the features for me, but you're not going to be graphing anything. I don't expect you to know what the graph looks like off the top of your head. Let's take a look at some vocabulary. Now they use limit and behavior, guys, but we're still going to use the regular and behavior concept that we've always talked about, but we're going to find out today that in rationals, the end behaviors of them refer to the horizontal and oblique asymptotes. Limit is as you approach a value, which is exactly what the end behavior looks like, right? It says like as x approaches negative infinity. So a limit exists because while you can't actually get to the value, like an asymptote perhaps, you are approaching it. So mathematical computation allows you to kind of like assume you're there, even though you're not really there. It's like dividing by 0. Like I can't divide by 0, but I can divide by something close to 0. Yeah. Same idea. That's what we're going to do today.
I also watched a really long video about that.
You must have a really exciting social life.
Oh, yeah, it's fantastic.
Those math videos are fascinating.
They are.
And they make them kind of fun, like us nerdy math people. Like
it was titled, "What if you put 0 to the power of 0?"
That's thought-provoking.
Fantastic. You should watch it.
Okay. So here's some, for many of us, brand new topics. So what does it mean when I want to find a vertical asymptote and a horizontal asymptote? Something we're going to talk about today. An oblique asymptote. Many of you don't know what that means yet. But here's some old topics. X-intercepts and Y-intercepts. We've done that before. So that should be familiar to you. Everything else can be totally new. But first, let's get some notation and concepts out of our way. These are not on your paper anywhere, but this is just a breakdown of what it means when I claim a function is top-heavy, bottom-heavy, or equal weight. So when we're going to discuss whether we have a horizontal asymptote or not, I'm going to ask you these questions. I'm going to say, is it top-heavy, is it bottom-heavy, or is it equal weight? And what you're going to do is you're going to compare the degree of the numerator to the degree of the denominator. So this is an x to the first power, right? And this one is an x to the second power. So is it top heavy, is it bottom heavy, or is it equal weight? This one is bottom heavy because there's a higher degree in the bottom of the fraction or the denominator than the numerator. So you get to use this little cheat sheet on your homework, and I'll give you a new copy for the test. When it's bottom heavy, it says that means you have a horizontal asymptote at y equals 0. We'll talk about y right now, but you don't need to like really understand this part. I'm just kind of talking to the people who are very interested in why that's true. A horizontal asymptote would be as you approach its end behavior. So as I go really far left and really far right. So I'm a positive lady. Let's talk about positive big numbers. What's a really big positive number? What? Okay, let's go with 1 million. All right. Last hour they were like 400. I was like, no, 1 million. Like 1 million's a big number, right? So if you plug in 1 million into this numerator, you get 1,000,006. Pretty big number, right? What happens when you plug it into the denominator? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 1 million squared, whatever that number is. Minus 3 million, which in comparison to that is pretty much nothing.
Isn't that just double? No.
No.
It's not. Oh my goodness.
Like, this is hard for kids to grasp, but like, I just think I wrote down 3 million. It's like nothing compared to this number. Yeah. I don't even know what this number is. I'd have to really think about that. And then obviously a plus 2 is like nothing.
Yeah.
Quadrillion, is that where we're at? I didn't even put commas. My daughter would be so ashamed of me. Okay, so if I took what is now relatively a pretty... Jeez, child, do you really...
Quadrillion.
Yeah.
There's 4 sets of 3 zeros.
Yeah. Quadrillion. Yep, that sounds right. Okay, so anyways, I never...
Wait,
million,
there's 4
billion.
sets
Oh,
of
that's,
3 zeros.
hold on.
That's what I was saying. Million, billion.
Thousands,
whoa,
million.
whoa.
It is trillion.
Oh,
Sorry.
Oh, once again.
Oh,
You're right,
schooled by
Cameron.
Cameron.
I'm sorry.
about
Forgive
that.
me.
You know what? This is the way I think of it. If I can't possibly like assume that amount of money exists in my pocket, I don't even want to talk about it. You know, like how many trillion? Oh, I'll never have a trillion of anything. All right. So I never thought I'd say this, but a million is pretty much nothing. It's very small when you compare it to a trillion.
Yeah.
It's not nothing to me.
With anything. If you
So-
compare it to anything.
So this is like the equivalent of like, I'm just going to throw a different problem out here. It's like saying take 1 and divide it by 1,000. Like you're taking something very small and you're dividing it by something very big. What happens to your decimals as you divide by bigger and bigger numbers? They get really, really, really tiny. Like almost to the point where they're
Non-existent.
nothing. So they're approaching a value of 0. That's why when you plug in really, really big numbers into a bottom-heavy fraction, you're approaching a value of 0 is what's happening. All right, equal weight. So this is an example of an equal weight fraction where your polynomial in the numerator and the denominator have the same degree. So when this happens, your horizontal asymptote is located at y equals the reduced version of the lead coefficients. So 2 over 1, better known as y equals 2. If you want the reason why that happens, and again, you don't have to memorize this, but some of you are moving on to calc, and this is part of calc. So if you plug in a million again, you have that 2 trillion over 1 trillion followed by stuff that really doesn't matter. Because when I asked you for a big number and you guys throw out a million, is that the biggest number out there? No. There's way bigger numbers than a million, obviously, since I can't count. So if you threw in an even bigger number, you'd see this discrepancy of like, these are pretty much nothing, even more so. So you're plugging in 2 trillion over 1 trillion. These are like negligible to the point where I don't even consider them. And then the trillions end up canceling each other out and you approach a value of 2 over 1, so 2. All right, and then if it's top heavy, which is this example here, we have a quadratic over a linear. This is just, you can't even think about this because that says a y. Top heavy, the number is just going to get bigger and bigger and bigger. Because if I took that trillion and I divided it by a million, but trillion's not even the biggest thing I could, use up there. It could be even bigger. It's just going to get bigger and bigger without bound. So we would say that there is no horizontal asymptote in that case. However, there is going to be what's called an oblique. There will be an oblique or a slant asymptote, which is part of my end behavior. All right, this is your yellow card. This is what you're going to use on every single problem we do today, every single homework assignment for tonight and the next night. And you're going to want to use in the exact same order that we're practicing. I'm really bad about staying in the order of the card, so if I deviate from the order, you let me know. Let's take a look at an example. This one is already, unfortunately this one's done for you, and it's done out of order. The card is made by Mrs. Hoffbauer with careful consideration to how we want you to approach them. And this is the way your book came up with everything, so we're going to go a little out of order, but we'll still answer them in order. So the very beginning of the card says, always factor P and Q first. So you look at your numerators and your denominators. Guys, do either of those factor? No, so we're good. All right. Next on the card it says, the domain is all real numbers except those that make the denominator equal to 0. So when I have to answer a question about domain, which I would do first, according to the card, what you do is you take your denominator, like you always do, and you tell me it can't equal 0. Well, y'all, what happens when you set that denominator equal to 0? You tell me that x can't be -3. Now look, finally, we're at that moment. Remember how I told you that eventually I'll let you be lazy? We're there.
Yeah.
You don't have to write interval notation anymore. You can just say domain x can't be -3. So then, if I look on the card, it says if x minus b is a factor in both the numerator and the denominator, you're going to have what's called a hole. So if you see a twin, top and bottom in your fraction, you have a hole. Do we have that situation going on right now? No. So move on. Number 4, it says if x minus b is a factor of the denominator but not a factor of the numerator, that means you have what's called a vertical asymptote. So the next thing we would do is identify the vertical asymptote. So you take your denominator and set it equal to 0, and you're going to get, now notice my notation here, guys, x equals -3. This is a line. X equals -3 is an equation of a line. It has to look like that. You can't just say vertical asymptote -3. That doesn't make any sense for this problem. Okay, it has to be a line. X equals -3. Now that kind of goes together with domain because the vertical asymptote is the physical representation for why your domain has been interrupted. So that's why we said our domain is everything but -3, because there's a vertical asymptote there. All right, next. So this is where it went a little out of order. I apologize. The next thing on the card says find your zeros or your x-intercepts. So your zeros / x-intercepts. Same thing, right? You're supposed to take your numerator and solve it by setting it equal to 0 and solving. So 2x minus 1 equals 0, which means we have an x-intercept at 1/2. But guys, what I want from you is to remember that for an x-intercept, while your x value is 1/2, your y value is 0. That's the definition of an x-intercept. I want this written as an ordered pair. The next thing on the list is your y-intercept. And then the card says it's when x equals 0. So this is just a matter of you, to use a little kid phrase, plugging in x equals 0 into your function. So 2 times 0 minus 1 over 0 plus 3. That reduces down to the fraction 1/3. But again, teacher wants you to write it as an ordered pair. So your y-intercept is at the ordered pair 0, -1/3. So I keep reading down the list, and then finally it gets to now compare the numerator and the denominator. Let's talk about horizontal asymptotes. So this fraction, I drew over it too much. Is it top heavy or bottom heavy or equal weight? What's going on here? It is equal weight. So because you have an equal weight where the degree in the numerator and denominator is the same, that means your horizontal asymptote is at the line y equals whatever the lead coefficient's reduced to. So that's why they came up with y equals 2. Now, this example is already drawn for you, but what I expect to see in your homework is probably you using graph paper, which we have a whole bunch back there. Every time you found an asymptote, what we're going to do is I'm going to take like a highlighter or a pen or something. I'm going to mark the asymptotes with that so I have a visual boundary. Every x-intercept and y-intercept I find, I'm going to plot them. Then at this point, you would use your calculator for some general shape help. I don't expect you guys to know what the shapes look like. And then y'all move on your merry little way. So your test on Friday, there's absolutely no graphing on it. You're just going to be finding all of these pertinent pieces, and you get to use your card, or a card that I give you. Okay? So it's all about practice, right? You got to practice using the card before any of this makes any sort of sense. So practice. Here we go. Practice this, y'all. Well, this is nice. Someone already kind of factored it for me. All right, let's go in the order of the card. Factor it. Check. It's already factored. So the next step is, it says the domain is the set of all real numbers that make the denominator equal 0. So for domain, you're going to check out your denominator pieces, and you're going to tell me what x cannot be. Can't be 0, and can't be 6. Very good. So something happens at x equals 0 and x equals 6 to create a discontinuity. We're at the bottom of worksheet 9A right now. All right, moving down my list on my yellow card, it says, if you have a factor that is in both the numerator and the denominator, you have a whole. So if I look at the numerator and the denominator, do we have any twin factors that are going to cancel out? No, we don't. So we're going to move on to number 4, which says, then you must have some vertical asymptotes. So the remaining factors in your denominator are the locations for your vertical asymptotes, and you can find them by setting the denominator equal to 0. You want to write yourself a little note. So that means you have a vertical asymptote at x equals 0, and you also have a vertical asymptote at x equals 6. And I think there's a bit of a misconception from kids when they look at this and they're like, oh, so domain and vertical asymptote are the same question? No. Every vertical asymptote will interrupt your domain, but we're going to find out in a minute there's other kinds of interruptions besides vertical asymptotes. All right, moving down my list. Now it says find all your zeros, also known as x-intercepts. So to find an x-intercept, if I'm just reading off the thing here, it says numerator equal to 0. All right, we got that. So numerator equal to 0 would be x plus 2 equals 0. So that gives you x equals -2. But teacher wants this written as an ordered pair. So if x equals -2, the intercept would have a y value of 0. All right, keep going down my list. Now I want the y-intercept. The y-intercept is found by, I know it's not the fancy term, but plug in x equals 0. So be careful here. You have a 0 plus 2 over a 0 times 0 minus 6. So it's 2 divided by 0, which is undefined. Anytime you divide by 0, and kids get this all the time where they're like, there's this, it doesn't like that. Even if this was 0 divided by 0, like you'd have to be worrisome about that because anything divided by 0 is undefined. So is there a y-intercept? No, there's none.
Wait, so is it? Oh, because there's a vertical asymptote at 0.
Yes.
So,
And I made a dumb mistake earlier, of course, in first hour. Poor first hour. That's probably why they're silent. They're just waiting for my dumb mistakes. But at first, I just got really confused, and I thought there's like an intercept at 0, and I was like, wait, but there's an asymptote. Like, that doesn't make sense. And then they're like, no, because I thought my numerator was x for some reason. It's not. All right, so we're moving down the list. Tell me whether this is top heavy, bottom heavy, or equal weight. Now, while it was really nice that they factored it for me, I need you to think about the degree of that denominator. You have an x to the first in the numerator, but what's going on in the denominator? It's an x to the second. So what is this? This is bottom heavy, and what does your little cheat sheet tell you about bottom heavy ones and their horizontal asymptotes? Yes, the horizontal asymptote is at y equals 0. All right, so now, and you don't have to worry about oblique because it's not top heavy. So now is the time for you to graph. Everything you just found, I want to see on your graph. So this is where I bust out the highlighters. And I'll take a highlighter and I'll mark off where the asymptotes are located. So like the vertical asymptotes at 0 and at 6. Oh man, that was really wrong.
man.
So close. Okay.
You just have to take it to 2.
It auto adjusts, but like I got a little weird at the end, you know. And then we just found a horizontal asymptote at y equals 0. And this is where another misconception is kind of born in Algebra 2. Sometimes kids think asymptotes are like magical fences that you can't touch or cross. That's not true. So an asymptote is what your function approaches on the very far extremes, whether it be on your domain or on your range. So it's not that it can't ever cross the asymptote, it's that once it approaches some very large negative or positive numbers, it's going to flatten out to that area. So like here, for example, we're going to show that there is an x-intercept at -2. Now this is counting by 2s, so sorry about that. We're not going to be able to graph a y-intercept because there isn't one. And when you go to graph this, you're going to see that it scoots along the asymptote here, but it actually comes through and crosses this intercept, and then it comes back to the asymptote. That happens sometimes. You don't have to know that off the top of your head. What you need to know is that an asymptote is not a fence. Okay? It's just at the end behavior on the far left side of that graph. It will be scooting along the asymptote, and at that point will not come back through and become positive. Yes?
You can teach it as a fence, though. Right?
We don't teach it in
I
Algebra
remember
2.
teaching it as a fence.
Yeah.
I remember it being
It's just the ones you guys do in Honors Algebra 2 is like a simplified version of it where, like, if we call the fence, at least you know, like, when you graph, don't get sloppy, you know? Yeah, but you probably didn't see any that came through and crossed, but they exist. Quite a few of them, and in PreCalc do this. We didn't do these in regular Algebra 2, but in Honors we did. In college algebra.
I don't know.
Not regular, though.
I remember.
Not on these. They were on logarithms.
Oh.
Those don't cross. A little different. All right, so a rational asymptote, you got to be careful because they aren't like fences where you cannot cross them. Okay. All right, so here, yeah, there's actually a funny Lord of the Rings meme for that. All right, so this one, notice it doesn't come back up to the axes because I didn't have any other x-intercepts, so don't be showing me that. And then this one, this branch doesn't go through at all. So I only know that because I didn't identify any other x-intercepts, and therefore it wouldn't be coming through the asymptote. This is a beautiful graph of Rousseau. That was almost right.
What did you say about Lord of the Rings?
There's a Lord of the Rings about thou shalt not pass.
No.
It's Gandalf, he goes, and he's the asymptote with his little staff. It's pretty cute. But that's not really true, so it kind of bothers me on some level. Yeah. Anywho. Guys, because we're short on time, we're just going to kind of, we have a gazillion examples that frankly we'll probably have to come back to revisit. So if you could flip to the back of your notes. And let's run through these 3 questions real fast because this is a good warm-up for like what we're going to have to do on Friday's test. So I'm not going to ask you to graph it, but I am going to have you find stuff. So find the domain and then tell me about any vertical or horizontal asymptotes. So we're skipping over the X and Y intercepts for these examples just for the sake of time, but for now this is a good warm-up, getting ready for our test on Friday. So the domain. Back at the top of the list it says make sure you factor everything. Talk to me about this denominator. Does this factor with real numbers? It does not. So when I ask you for domain, and I say, well, it's when my denominator can't be 0. Well, if you tried to solve that, you'd get the square root of -1, which is an I plus and minus I, but not real, right? So I wouldn't be graphing a non-real asymptote. Therefore, there is no interruption into the domain, which means your domain goes forever. The same thing will affect my answer for the vertical asymptote. I wouldn't be able to set my denominator equal to 0 and actually find the location for a vertical asymptote because there are none. But horizontal asymptote you can answer for me. Is this top heavy, bottom heavy, or equal weight? This is bottom heavy. So what does your little cheat sheet say about bottom heavy ones? At y equals 0. So make sure you give me the equation y equals 0. Don't just say 0. Alright, same idea here for number 2. This time you do have a domain interruption in the form of a vertical asymptote. So your domain would be that x can't be -1, and the reason for that is because y'all have a vertical asymptote at x equals -1. Make sure it's an equation. Is this a top heavy, a bottom heavy, or an equal weight one? Alright, so since it is equal weight, very good. You look at your lead coefficients for those leading terms there, you get y equals 2. Nice. This one, like, they're trying to be nice by factoring it for you, but you do have to remember that it's factored when you get to the last question here. The domain, I see 2 interruptions. X can't be -1, and x can't be 2. Now in this example, the reason it can't be -1 or 2 is because you have 2 different vertical asymptotes. You have a vertical asymptote at x equals -1, and another vertical asymptote at x equals 2. And then horizontal asymptote, now be careful, it is factored form, so this is secretly an x over an x squared. So that's bottom heavy, which means what? Y equals 0 is the location for your horizontal asymptote. What that means in using old terms, guys, your branches, if you look at their end behaviors, they'll be flattening out at y equals 0 on both ends, okay? Notice we have not talked about top heavy yet. We probably won't get to that until tomorrow, I'm going to be honest, but we'll see. All right. I got to skip around a little, sorry. This guy. All right, next on your notes, it says, let's talk about what happens when you have a hole. Because on our chart here, our tape, what is this called? Reference sheet. This little like 1, 2, 3, 4 thing. It talks on number 3 about if x minus b is a factor in both the numerator and the denominator, then there's going to be a hole in your graph. And you're like, what? I've never seen a hole in a graph. And I think that's not true. I think you have seen a hole in a graph before, maybe not a rational function. But here's some vocab for you. So while we call it a hole, because it literally looks like a hole, it is a discontinuity in your graph. So it's officially known as a removable discontinuity. So you know math, how like we name things for exactly what they are? This is another case of that. So if you think about algebra and you factor a polynomial over a polynomial and you have a twin set of factors that crosses off, that's what it looks like in math when you remove something. You cancel it out, right? So, hey Bob, what do you want to call this? A removable discontinuity? Okay, cool. All right, so it still affects the domain. There's something wrong with your graph at that value. It's not going to be a vertical asymptote though. So that's why Mrs. Hoffbauer was careful to have you talk about domain before you come through and you cross off any of these discontinuities. All right, so here's what's going to happen. We're going to see an example where, and this is I think on your yellow sheet, it tells you like exactly what to do. So once you factor and you cancel because you have a hole, then you're going to be plugging everything back into the new simplified equation, the reduced rational. So what I kind of think about on this set of steps, once I get to that step, and I've talked about like where the hole is and everything after that, I no longer look at my original function anymore. I'm just going to look at this new reduced one, which is going to be nice because it's going to be real small. You're going to love it. Okay? Here we go. This one's already half done for you, which is kind of lame. But if I go through my steps on my yellow card, the first thing it says to do is factor everything. So this right here, before they did any canceling, was the factored version of this polynomial, or this rational, excuse me. So then it says to talk about domain next. We all get a little cross-off happy because you're like, ah, factors cancel, there's a hole. That's not yet. That's not till number 3. So number 2 says, talk to me about problems with your domain. And this is where kids get confused. This, I know it's going to cancel in a minute, but it's still a problem with your domain. So x can't be -2 and x can't be 4. So now I'm on number 3, where it says, if you can remove the discontinuity like this, that means you have a hole. So the hole is an ordered pair location. Where do you suppose the x value is for this ordered pair? Yes, it's at -2. And then you're like, well, heck, how do I find the y value? So you go now to the new version of your polynomial, which is what's left after you remove the discontinuity. So, gosh, I keep calling it polynomial. I'm so confused. The rational function. The new rational function is x minus 2 over x minus 4. From here forth, that's the one I want you to look at. Don't go back to the original one anymore. So if x equals -2 gets plugged into this new reduced rational function, you get -2 minus 2 over -2 minus 4, and you get -4 over -6, so you get a 2/3. So there's a hole at -2, 2/3. The hole will not be visible on your calculator. In fact, if you tried to plug in x equals -2, it would say error if you had the full one in, right? Not the reduced one, but the full one. All right, so from here on, you guys can use this new little blue version of the rational. Don't go back to the original. What's next? Vertical asymptote? All right, so vertical asymptotes are found by taking your denominators and setting them equal to 0. But I'm going to refer to this new guy. Because if I go back to the original one, I'm going to get confused. And I'm going to say that there's a hole and a vertical asymptote at -2. And that's not true. So there's a vertical asymptote at x equals 4. And then the next thing in the list talks about X-Intercepts, which we know we can set our numerator equal to 0. So again, I'm going to go to this new version. And I'm going to say x minus 2 equals 0. Which means you have an x-intercept at 2, 0. Notice I didn't go back up to the original because there's a hole at that other one, so don't use it. What are we left with? Y-intercept now? Y-intercept, I'm just going to go back to this version. And if I plug in a 0 for all my x's, I get -2 over -4, which is a 1/2. Notice I'm writing all my intercepts as ordered pairs. That's important. Okay. So what's next? Horizontal asymptote. Again, I'm just going to go back to this version. Is it top heavy? Is it bottom heavy? Or is it equal weight? It's equal weight. So if you have an equal weight rational function, that means your horizontal asymptote is at y equals and then the reduced version of the lead coefficients. So for us, that'd be a y equals 1. So you kind of get the flow of the yellow card. It does make sense. Like, it took me a while to get used to it because it's not necessarily the way that I think about it, but it's because I have this vast, deep knowledge of rational functions that you guys don't have yet. Okay. All right. So we haven't talked about slant or oblique asymptotes yet. I think we'll have to save that part for tomorrow. Let's try one more real quick, guys. Ooh, 4 looks fun. Yeah, we can get this done in a few minutes, okay? That's way out of order of my card, man. All right. Oh, that's a nice little hint. It says, if you just graph the denominator only, She claims that you can just find the zeros at -3, 1, and 2. So that's nice. You could factor by grouping as well. No, you can't. No, thank you. All right, so we're just going to use her little cheat sheet thing. I would never give you a denominator that you couldn't factor easily. So, I don't know what she's thinking. Sorry, Hoffbauer. That was a weird problem that we came up with. All right, x plus 1 and x minus 2. Notice what I did there is I took our zeros and I put them back into factored form. Now this numerator I can totally factor. I'm doing step 1 on the card, right? I'm factoring everything. So is this x minus 7 and x plus 3? I really shouldn't write over text. This is a bad idea.
Especially with
the same color too. This is awful. Okay, so don't cross anything off yet. Because I see it too. There is a removable discontinuity here, but don't do it yet, because first, it says to discuss your domain. Guys, we got a lot of domain problems. You got 1, 2, 3 problems. So x can't be -3, can't be -1, and can't be 2. The reason for that is because there's some form of discontinuity at all 3 of those. Now let's talk about the fact that yes, there is something that totally reduces. The x plus 3's are going to remove. So since x plus 3 is the factor that you canceled out, that means you have a hole at x equals -3. But we got to find the y still. So now I'm going to give my reduced version of this guy, who still has an x minus 7 in the numerator, and it still has an x plus 1 over x minus 2 in the denominator, times x minus 2. Okay, so from here forth, only look at this reduced simplified version of the rational. Did I call it a polynomial again a minute ago? Gosh, I quit. All right, plug in a -3, guys. So a -3 right here, and right here, and right here. Oh, that's a lot of mental math. Here we go. -3 minus 7 is -10. What is this? A -2 times, does that say -2? Times -5. Oh, that's not too bad. -10 over 10? -1? Cool beans. All right, here's what I'd like to do. I'd like to graph a hole at -3, -1. Nailed it. No, it's open circle. All right, now we can talk about vertical asymptotes, because when I refer back to this version, I can see my 2 vertical asymptotes. What are they? Where are they, I should say? At x equals -1 and x equals 2. So I'm going to bust out my highlighter, and I'm going to graph a vertical asymptote at x equals -1, kind of, and then at x equals 2. Now notice, I didn't put an asymptote at x equals -3, which is the mistake that a lot of kids do, because they're like, denominator is all vertical. No, sometimes they're holes, so be careful. Where are we at in the list? Vertical asymptote. Oh, X-Intercept and Y-Intercept. All right, so X-Intercept. Well, I would take my reduced version and set my numerator equal to 0. So that means x equals 7 is an X-Intercept. Oops, kind of graphing on my own thing here. And then my Y-Intercept would be a plug-in x equals 0 moment. And again, go back to the reduced version. Well, that's a lot of thinking. Okay, so that's -7 over 1 times -2. So -7 over -2 is 7/2. You can call that 3.5, of course. So we have a y-intercept at 3.5. And then one more thing, I want to know about the horizontal asymptote. I would look at just the reduced version. It doesn't really matter though, but I would look at the reduced version just for process. You have a x to the first over x squared. So we have a bottom heavy, which means you have a horizontal asymptote at y equals 0. So I would bust out my highlighter one more time, and I draw a little fence, if you will, at y equals 0. And then from here, guys, I would not in any planet decide like, yes, you all know what this looks like. You would have typed this baby, the original one, into your calculator, And you would have got some assistance from your calculator at this point, okay? This is a really funky looking one. It looks like this. It has 3 parts to it. And like I said, oh geez, I missed my point totally. This is looking like a parabola in the middle. I don't know what I graphed. And then up here, this branch comes down and then crosses through at 7. Yuck. Okay, we'll do a little more of that tomorrow.